So we can all agree that New Zealand is a pretty great place, right? But everywhere has its issues. Nowhere is without its faults. And one of these issues that is currently facing New Zealand is bovine tuberculosis. Bovine TB is a respiratory disease that can prove fatal, and it comes into our systems via the consumption of milk from infected cattle. Each year, the dairy industry brings in approximately $14 billion to New Zealand. But the first issues that we see when we think about bovine TB in relation to this are ones of consumer confidence. First of all, we see that people really probably won't want to buy a product that has the capacity to kill them, and that's a pretty reasonable feeling. The second issue is that because of the presence of bovine TB within New Zealand, our #1 trading partner, Australia, refuses to buy live cattle from us. And then the third issue that we see is the answer to TB that we currently have, which is when we discover its presence within herds, we wipe out the entire herd, even if just one cow proves to be infected, thereby damaging the livelihoods of farmers up and down New Zealand. But how do we have bovine tuberculosis in New Zealand? What is its carrier and what spreads it? The answer to that is possums. So, as we know, possums aren't just an issue because they're a vector for bovine tuberculosis. They have a wide variety of impacts, most of all on New Zealand's biodiversity. What they do is they kill our native birds in their nests. They are a scourge upon our native plants, and all of these have impacts on our environment and our native taonga. So, how do we win this battle for the birds? How do we win this battle for the bovines? Well, our current answer to this is 1080. But what 1080 is really a sledgehammer to smash a nut, a gold-plated sledgehammer at that, as it costs $80 million a year to use. And when it was first introduced, they told us that it would eliminate possums by 2003. But here we are, 14 years later, and experts are telling us that predator-free by 2050 is looking like it's not going to happen. So at this point, we can all acknowledge that the game has to change, right? And my proposed answer to this is at the forefront of scientific research. Ladies and gentlemen, allow me to introduce you to CRISPR-Cas9. So CRISPR-Cas9 comes from an ancient bacterial immune system, and it works in two halves. The first half is CRISPR, which stands for clustered, regularly interspaced, palindromic repeats. So you can understand why they've chosen to abbreviate that. And it looks nothing like this. So what CRISPR really is a rogues gallery, a mugshot gallery of the viruses that the bacteria has previously encountered. And after it defeats them, what it does is it stores sections of their DNA in these databanks, like mugshots, so it recognizes them when it encounters them again. And when it does encounter them again, the Cas9 enzyme is released. The Cas9 enzyme then partners itself with a section of guide RNA taken from the mugshot gallery that is CRISPR, and it becomes something of a guided missile. Now, this guided missile then seeks out sections of the DNA that match the guide RNA, and what the Cas9 enzyme does is it cuts them out. In organisms with one chromosome, this kills them, but that's not what we're here to talk about. What we want to do is see what it does to organisms with two chromosomes, right? And what it does to these is it triggers the repair process. Now, this repair process involves the still intact chromosome overlaying itself over the damaged one, and using the information in the one that still works, it fills in this blank. But what scientists have found a way to do is they've found a way to insert a new trait, a trait that we want to see, in between this repair process. So what happens is it fills in the blank with the trait that the scientists and that we want to see within this organism. So instead of just removing a trait, what we do is we alter it, effectively biohacking the organism and cutting, copying, and pasting a new trait into the organism. But what we don't want to do, we don't want to just alter one individual, because that's never going to make a difference to anything, right? What we want to do is we want to impact the whole population and cause something of a domino effect. And to do this, we can employ CRISPR-Cas9 as a gene drive. What gene drives do is they usurp the usual 50-50 inheritance rules that we see in nature. This is done by injecting CRISPR-Cas9 into the germline of the organism, so it changes both of the chromosomes in the organism instead of just one. On top of this, CRISPR-Cas9 then writes itself into these chromosomes, so it's there next to the trait as well. So not only is this new trait passed on to the next generation, what we see is CRISPR-Cas9 is passed on too. So it works its magic in the next generation and in every single generation following. But how does that help us? This chart shows an experiment that was done with mosquitoes a few years back, and on it, blue equals male and green female. As you can see, something does look a little off with this, right? And that's because in this experiment, the males, the blue mosquitoes, were altered to only produce male offspring, who could only produce male offspring, and so on and so forth. And what this meant, and as you can see, after a while, the number of males to females became so high that the population was no longer sustainable, it crashed, and the colony was wiped out. And ladies and gentlemen, this is my answer to possums. It's the utilization of CRISPR-Cas9 as a gene drive to introduce gender biases into the species. But why is this better than 1080? Why is this better than what we've already got? CRISPR-Cas9 is a much more targeted approach than 1080. It's not carpet bombing sections of the bush from helicopters like 1080 does, and it only kills what we want it to, right? We choose one species, and that species is the only thing that gets affected. We won't see things like our pets dying after they eat the carcasses of a possum, which has been killed by 1080. We won't do things like killing the birds we are supposedly protecting when they consume these poisonous pellets. Also, it allows us to reach locations that normally we may struggle to do, as in effect, what we are doing is getting the possums to do the legwork for us. It doesn't put poison into our own food chain like 1080 has the capacity to do, and it's a whole lot cheaper. So when we eliminate the possums, we see things like our native flora and fauna thriving and coming back. But that's not where the benefits of CRISPR-Cas9 end. It has a whole lot of other applications. So we've been seeing up and down New Zealand the myrtle, pukutahawa, and ramarama trees facing localized extinctions due to fungus. And currently we don't actually have an answer to these fungus other than slow resistance breeding, which takes decades and just doesn't work in the time frames that we want it to. But CRISPR-Cas9 has been floated as an answer to this fungus. It also has a variety of medical applications, right? Research has suggested that it could fight cancer, it could cure Alzheimer's, and it could possibly fight various heritable diseases. But if CRISPR-Cas9 is so brilliant, why don't we already have it? So first of all, there is a patent battle ongoing between Harvard and Berkeley to decide who actually owns the thing. But once this is solved, then you can bet your bottom dollar that this will see application on an industrial scale. It's also developing technology, so not everyone fully understands the implications of its use yet. We don't fully understand the ripple effects that may come from its release into the wild, so as such, no one's really going to want to release it until they know that. But probably our biggest issue that we see when it comes to the application of CRISPR-Cas9 here in New Zealand is our clean green attitude. Because there is a great deal of anti-GM sentiment in New Zealand, and there is a societal attitude that means that any suggestion of GM is automatically shunned. Indeed, the Parliamentary Commissioner for the Environment, in their report on 1080, concluded that biological controls, things like CRISPR-Cas9, were probably the way forward in combating pests, and that they were the next step up from 1080. But they also concluded that these would not probably end up making it into use because the public sentiment against them is so great. But in order to see a shift in these societal attitudes, we need organizations like the Ministry for Primary Industries, like the Environmental Protection Authority, to initiate a public and official discussion on the applications of CRISPR-Cas9 in things like fighting possums, in things like medical application. And when you start doing that, when you start having these informed debates, that is when you can see the sparks of change beginning to occur. But even if we don't end up accepting CRISPR-Cas9, even if the public deems that the cons outweigh the pros and that we don't want it and we don't want any genetic modification, then we see that organizations like MPI, like EPA, do need to adopt new legal frameworks in order to govern how they interact with other countries that use CRISPR-Cas9, how they govern the use of CRISPR-Cas9 possibly coming into New Zealand. Because in places like North America, we're seeing CRISPR-Cas9 being approved for medical trials. We see that if any of us in this room go online right now, we can order a CRISPR-Cas9 kit for $160 delivered to our door. And if EPA and MPI don't shift to this changing world, then that poses a whole variety of risks, right? And then we have our other issue, Australia. So, as we all know, possums are a protected species in Australia. They like their possums over there, unlike us. But if we accidentally wipe out their possums by some of our altered specimens making their way over there, then it's not going to matter that they are perfectly able to buy our cattle, because they're simply not going to want to, right? But this isn't the kind of the be-all and end-all of this issue. There are a variety of answers that we can do in relation to them. We could engineer CRISPR-Cas9 with a kill switch that means it dies out after a few generations. Or we could give the Australians a reverse-engineered version of our complex, which means they can effectively inoculate their own possums against it. But despite these issues, CRISPR-Cas9 is a viable solution to bovine tuberculosis in New Zealand, to possums and to other pests, and to a myriad of medical issues that have plagued mankind for so long, and quite possibly the push that we need to have a robust and informed debate about the future of genetic modification in New Zealand. Ladies and gentlemen, I truly believe that with CRISPR-Cas9, the possibilities are endless. Thank you.
Thanks, Isaac. I'm asked by my more scientific colleague to ask you about resistance caused by DNA repair mechanisms other than CRISPR. Any idea what he's talking about?
Sorry, is that the resistance to CRISPR kind of being formed in the population?
Yes.
So that is a risk, and it's one that some of the scientific trials with mosquitoes have turned up. But what my reading suggests that they are able to do is they are able to kind of introduce refresher doses almost of CRISPR-Cas9 into the population, and that's something that we'd probably have to do with possums, is we'd have to, at regular intervals, catch and release possums after altering them again with the complex, just to ensure that it keeps going, as it could die out, yes.
This is genetic modification, right?
Yeah.
No question about that. Just by the way, if I ordered my CRISPR-Cas9 kit online for $160, what would I do with it?
Well, that would depend on the varying degrees of aptitude, but it is possible that you could alter certain specimens, certain very simple specimens, but to truly fully engineer a species, you would need access to a lab.
Right. So I'm not going to cure the possum problem in my own kitchen.
It's highly unlikely.
Okay. What are the consequences, Isaac, of literally wiping out a species?
So that is a grey area, and it's not one that I can say I know all of the answers to. But if we look at places like Zealandia, we look at places like Somes Island in New Zealand, where they have removed all pests from the environment, it's from places like that we can get a pretty good idea of the impacts on the rest of New Zealand. So we'd see things like our flora and fauna returning, and we've not seen, localized apocalypses in those zones. So we can conclude that it would probably actually be pretty good in terms of removing possums. It is possible if you removed, some species which are not possums, which are not pests, then you may see negative impacts. But in that way, you do have to be very selective and very careful about what you target with this technology.
Thank you.
So thank you.